Swayam Prabha. Digital India. Educated India.
Can you give me some points? Okay, I'll repeat the question again. So if I want to do something useful with my qubit, or with this entire way of processing information, right? We're storing information in a different way and processing it. What are the things that as an experimenter I should be able to do with a qubit? Yeah, so manipulating, right? Manipulating. What else should I be able to do? So basically, you should be able to, you have to be able to recast your problem into a bunch of qubits. That's correct, very good. And then you said we have to be able to manipulate by rotations. Very good. We should be able to measure them. What else should we be able to do? Hmm? What do you mean by efficiency? Okay, it's faster. Yes, we want it to be useful so that we can do it in lesser operations. But when I say faster, right, what am I trying to compare it with? That's one thing. But also for the qubit itself to be useful, right? A qubit may not be perfect, right? It may have losses. I try to prepare some state, and at some point, there is some noise in the system and it just dies. What I prepared just died, and then I have no longer access to the state I prepared. Say I prepare a superposition on the equator, but because of some thing I can't control, this basically decayed. Okay, if this decays, then basically I've lost the information I stored. Okay, so real world qubits are not perfect. Okay, they suffer from decay and decoherence. Okay, so what we want is also the ability to prolong the what is called the coherence time of the qubit. Like how long can it coherently remain in a superposition that I prepared? Especially imagine that you are you have a bunch of you have a billion qubits and you do something on the first million qubits, and then you go somewhere else, do something, and by the time you come back to those million qubits, they're gone. Okay, they just decayed. Then what's the point of doing all of this, right? So you need to be able to store them for long enough for the entire duration of your calculation, right? So you need to have a long coherence time. That's a good quality qubit, right? And then the other thing that you should be able to do, if you think about it, is if I want to repeat that calculation, I must be able to consistently come back to that same state. I need to have some initialization or reset method so that I keep coming back to that same state so that I can repeat that calculation or a similar calculation. Here by coherence I simply mean the ability to maintain a particular superposition in a relative phase that I wanted it to be in. So coherence simply means the ability to maintain a particular superposition that I want. That's all here. Okay, we're using it in a very loose way. Okay, so that's one more thing that we need to do. And so basically we have to find an efficient way to reset, okay, and initialize the system. And we need it to be clean. What I mean by clean is we don't want it to be noisy. Okay, if your qubits have a lot of noise, they randomly jump from 0 to 1 or 1 to 0, or there are other things in your system that is affecting the qubit. You want to eliminate all of these things. Okay, so in some sense you want to go into a state that has not so much disorder, or into a low entropy state, right? And then the other important thing is the real power of quantum computing comes when qubits interact with each other and you are able to prepare superpositions of joint states of qubits. Okay, so what I mean by that is as a simple example, and I won't give you much math, so if you don't understand all of it, it's fine. So if I take two different qubits, right, and I prepare them both, let's say in this very same state. Okay, so one way to write that state is, I want to erase some portion here, so let me erase this. Okay, so then I can basically write it, okay, as something like this. This is the state, and this I would write as 1/2 0 0 0 1 1 0 1 1. Okay, this is basically two qubits both in this state. Okay, I just basically multiplied their coefficients together and basically wrote this as a product and multiplied it out. Okay, so now you know that this state came from here, right? So, and that means that we know that we could factorize this state like this. Very strictly speaking, this operation that I'm doing here, this is called a tensor product. Okay, I won't go into what that means. That's a whole separate lecture on its own. But what it means is that at this point, I'm just multiplying out the various combinations and I can write it like this. But I know that I could always represent it as two qubits, each one in a particular state, and I could specify the state of one qubit without necessarily specifying the state of the other qubit, right? So what that means is this qubit is in state psi1, the second qubit is also in state psi1. I don't have to tell you that qubit 1 is in state psi1 for qubit 2 to be in state psi1. Okay, they're basically independent pieces of information. This is in psi1, this is in psi1. Okay, now I'll do a very small tweak. Okay, and the tweak I'm going to do is basically write this with a minus sign. Okay, there is a plus sign here. I'm going to put a minus sign here. Okay, because this is again some state in some four-dimensional space with the possible basis vectors 0 0 0 1 1 0 and 1 1. And what I've done there is taken a superposition of four different basis states and I've put a different relative phase to what I had before. Okay, that's all I've done. Try to factorize this. Can you factorize it for me into two states that look like this, into two different, or maybe would you get this state if I did something like this? Right, you would get more minus signs, right? You would actually get minus, minus and plus, right? So actually there is no way to write this as a factorized state. Okay, so entanglement is this, that I cannot write down a state of a multi-qubit system into factorized states of separate qubits, right? I really cannot specify separately the state of qubit 1 and qubit 2. I really need to specify them together. Okay, there is no way to factorize, and that is an entangled state. It's basically a superposition in the joint space of the different qubits. So superposition in some sense is more fundamental, so but that's where entanglement comes from. Okay, so I need to be able to prepare states like this, and for that I need my qubits to interact. Okay, so that's the other requirement. Okay, so if you ever look this up, there is actually a very nice set of criteria for how to build a quantum computer, and it's basically the things that you all said. Okay, but it was said like 25 years ago or something. Just one second. So I wanted to go look up something that's called this. Okay, DiVincenzo criteria. So David DiVincenzo is a pioneer of quantum computing, and he came up with a set of criteria which essentially has all the ingredients all of you said plus what I just said about the ability to entangle qubits, and these are some kind of basic requirements that I need to be able to do as an experimenter in order to realize a functioning quantum device. Okay, so just look that up and I think you'll find it interesting. Okay, because it allows you to do so that's a different story. What you can do with it is that, for example, in the context of sensing, right, you can actually sense more precisely if you have entangled states. That's something I won't tell you how. And for example, if I want to be able to simulate these electronic systems, chemistry systems, you can map your initial state onto a set of qubits, but if I want to study the dynamics of that system, I need to get the qubits to interact. And interactions happen through entangling gates like this. Okay, so the whole reason why chemical systems are hard, for example, is because electrons are correlated; they interact with each other. So the ability to simulate interactions is very crucial. So typically what happens is, yes, you can, if you have the right set of gates. An entangling gate can entangle, but it can also disentangle for you an entangled state. Yes, you can do that. And typically when I have imperfections in my system, these kind of entangled states are fragile. So they will basically, become unentangled states because of the dissipation processes.
Unentanglement, you losing the data from the entanglement.
It depends what you want to do. It really depends on the task at hand. So you have to think about what is the particular protocol in mind, at what stage is entanglement useful, and when should I convert it back to something that looks like a factorized state and so on. Okay.
And adding on to what you said about the information loss, would it entangling cause you to lose information? Because when you have two different states, you need a lot of different variables to represent. But if those two different things have these two different qubits are the same state.
No, think about how many parameters you need here, right? Over here in a factorized state, I need 2 parameters here and 2 parameters here. So that's basically 4 parameters, right? For every state. Here you need more parameters if you think about it. I have 3 populations. The 4th one is normalized, right? But then I have 3 relative phases as well, right? 1, 2, 3. I can put a E. So I actually have 6 parameters here. So you actually have more combinations here, then this is a restricted subset of the possible states here.
So we said prepare qubits. What do you mean by preparing?
Probably what I meant was initialize or reset a qubit. So prepare it in a particular state, meaning that I have all these possible states, and every time I start some computation, I want to start in a particular state, right? And that means I prepare the state of the qubit.
So we said build quantum computers first. How is that possible?
We will see now. So with that, I want to show you one particular device. I'm going to use my slide. So that's one example of how you can build a quantum computer. Okay, so these are called trapped ions. Have you heard of this? No. Very good. I'm very happy that you haven't heard of something that I know of. Okay, so this is not what something like IBM or Google do. They use another technology called superconducting qubits, right? This is basically working with real atoms. Okay, so what you're seeing here, each and every dot over here is basically one particular atom. It's really one atom. You shine a laser on it and it fluoresces. Okay, and you can basically capture the fluorescence, and if you have a proper imaging system, you can basically make an image of a chain of charged particles like this. Okay, so different species are used. Okay, so and there are different types of traps, but all of them have one common working principle, which is that these are all singly charged particles. Each one is a singly charged particle. For example, in this trap, which I have done some work on, each ion is a beryllium ion. Okay, it's actually the element beryllium, singly charged. You remove one electron from it, and then it becomes a charged particle which you can trap with electromagnetic fields. Okay, so these are called ion crystals. Okay, and you can have very long strings of ion crystals. Okay, that have been realized in different labs. I've also shown you which universities and where, right? And you can have 2-dimensional crystals, and people are also working towards making 3-dimensional crystals, and this is one platform using which quantum computers are made. Okay, like I said, if you want to build a quantum computer, your elementary particles have to be, or your elementary building blocks have to be units that actually obey the laws of quantum mechanics. And here these atoms are the ones, each atom basically encodes a qubit. We will see how. Just like how you had a head and a tail encoding a bit, each atom actually is able to encode a qubit over here. Okay, but before going into how these are encoded, I want to basically, where's my computer? It need not be charged to be encoded. That's a very good question. They're charged here because it provides you one way to trap them. They don't fly away, right? Like if I want to work with an atom, right, I can't hold it in my hand. It has to be trapped using some external fields, right? And if they're charged, I can manipulate them with electromagnetic fields. So one question that I want to ask you here is, if I give you purely electrostatic fields, okay, purely electrostatic fields. Do you think I could build an ion trap? What do you know about stable equilibriums and
That would be unstable.
electrostatic fields?
I think putting all of these different ions in an electrostatic field is very unstable equilibrium because you want to get away from the as soon as possible.
So the question is, can you make a stable equilibrium, even fundamentally, with an electrostatic field? Sorry, I heard something. Have you guys? Sorry, say that again. Why? Why can't I do this with purely electrostatic fields? Well, that's not. Well, I want them to be static. So why should I need something?
But initially they're not. So to bring them to that static
Say I've done something, and then I have brought them. They are initially stationary, and now I put some static fields. Can I have a stable equilibrium?
A very simple example of a dipole. The dipole that is aligned with the electrostatic field would be in a stable equilibrium.
Well, you're always assuming that the dipole is. Well, they're all. In this case, they all have the same charge. But the basic point is there's something called Earnshaw's theorem. Have you guys heard of this? No? So what that says is that you can't have a configuration of charges in stable equilibrium under purely electrostatic fields. Okay, and the reason for that is quite simple. It's a theorem, but the reason is simply that your electrostatic fields are coming from some source. Okay, and in free space you have some field lines coming from this electrode configuration. You have some field lines, right? But remember from Gauss's law that Gauss's law, yeah. So if I don't have any charge in a region, all the field lines that go in should come out, right? So if I put a test charge there, right, I can never have field lines that try to confine it everywhere. Okay, what goes in must come out, so it will always get pushed further away. So I can never have a stable equilibrium under purely electrostatic fields. Okay, so this is never possible. So what ion trappers do is kind of clever. What do you think you can do? Earnshaw, earn like earn money, Earnshaw, yeah. So, currents? So I'm interpreting that as time-dependent fields. Okay, is that what you mean? No.
Yes.
Okay. So basically, there are two ways to do this. Okay, I only said electrostatics. I didn't say anything about a magnetic field. So I can either add a magnetic field on top of the electrostatic field, or I can have a time dependent field. Okay, and both of these are actually used. Okay, so a time dependent field is an electric field that's oscillating in time, like our current carrying wires. We have 60 hertz current oscillations, right? That's what we use. So an AC field basically. Okay, so these are the two types of devices that are used, okay, for trapping ions. Okay, one of them is called an RF Paul trap. Paul is basically the name of the scientist who basically pioneered this technology. RF stands for radio frequency, and the reason for that is you apply radio frequency electric fields over here. Radio frequency, what's the kind of frequency in hertz for radio frequencies? Do you have a feel for what a radio frequency is?
It's a big number. I think it's not 10.
In hertz.
Words.
So a radio frequency is of the order of a megahertz. Okay, that's 10 power 6 oscillations per second. What's the frequency of visible light? Yes, convert to hertz. That's gigahertz, that's microwave. That's not visible. That's what you would use in your microwave oven, for example. What about visible light? Kilohertz is very weak. Kilohertz is what we can hear. That's our range. Someone said terahertz. Yeah, it's hundreds of terahertz. Terahertz is 10 power 12. Visible light is more like 10 power 14, 10 power 15 hertz. So these three things I want you to remember, okay? You should tell this in your sleep. Radio frequency 10 power 6 hertz. Microwave gigahertz 10 power 9. Visible 10 power 14, 15. Okay, this is the kind of separation of frequency scales. Okay, so In this device, you actually have all these things. This is actually called what is called a blade trap. Okay, this is a particular type of trap, and that's because of the way these electrodes are arranged. These electrodes here, they provide some static potential, okay, and they push the ions inwards along the direction that they are aligned in. Okay, so you get confinement like this, and you apply, and these are static electrostatic fields, but those electrodes have a time dependent field. Okay, so what I do is I apply plus voltage here, plus here, and minus here and minus here on the diagonally opposite points. Okay, and then I rapidly change the phase of the voltage applied. Okay, I do this really quickly. So what happens is at one instant of time, I have a confining potential along one direction and a deconfining potential in the other. So the ion tries to move in that direction, but very quickly I flip the sign, then I get something confining in this direction. So by this way, by the time the ion has any time to move, I'm always continuously trapping it in some kind of dynamical trap, right? And that's the way that you use a time dependent field to trap it. Think of it like a saddle. Okay, a saddle has a slope like this, but also a slope like this, right? And that means that if I keep a ball in the middle, it can roll this way, but it's confined this way. But by the time it rolls a bit, if I change the direction of the saddle, it's confined, right? And then it's deconfined in the other direction, but I very quickly change it again, right? So continuously I'm kind of storing it in that central region associated with the saddle. Okay, so this is tens of megahertz, that's why it's called RF. Okay, this is a rotation, so tens of megahertz means about 10 power 7 oscillations per second. That's how fast it's done. Okay, all the light that we have here is also oscillating at 10 power 15. We can control radio frequencies very well. I mean, radio frequencies we have been controlling since the time of Marconi, right? So our technologies are very mature for that. So that's not so much of a challenge. Okay, so that's one way to confine ions. Okay, and you can see that there is a crystal that is being formed here. Okay, by crystal I mean that there is some ordered arrangement. They're not in some random pattern. How do you think this ordered arrangement arises? Where is this ordering coming from? What are the forces that are balancing?
Repulsion between them makes them equally spaced and they can't move in any other direction.
So yes, so what happens is that there is a confining force coming from the traps that you put in, but all of them have the same charge, so that means they repel each other, right? So there is a balance of the confining force and the Coulombic repulsion between the ions, and that leads to the formation of these types of crystals. Okay, and whether you get a 1D crystal or a 2D crystal like in the previous slide, okay, this really depends on the parameters with which you trap. Okay, how strong is your trapping in different directions. If I make my trapping say in the XY plane very weak and the trapping in the Z direction very strong, then naturally the crystal will kind of spread out very beautifully in the XY plane, and then I get a planar crystal like this over here. Okay, or rather over here. Okay, this is done in a Paul trap. This is actually from a penning trap. This is the second device that I wanted to mention, and this is the device where instead of using time dependent electric fields, what you do is you supplement your static electric field with a magnetic field. Okay, and this is not some simple magnetic field, it's actually coming from a superconducting magnet. Can you guess how strong the magnetic field is? No, that's too much. That's too many Teslas. 1 Tesla is already, it's of the order of 5 Tesla. Okay, it's of the order of 5 Tesla. 1 Tesla is already too much. It's something that we will not withstand as human beings. If you have ever visited an NMR lab, they will tell you to remove. What is 9.41? Yeah. So there, they will. You might have noticed they will ask you to remove any jewelry or belt, all these things. So that's for safety, right? Watches and things like that. So similarly here, there is a superconducting magnet sitting at the top, which I haven't shown here. Okay, and that's supplying this very large magnetic field of about 4.5 Tesla. Okay, so what happens here is all these circles that you see here, I'm showing you the cross section of electrodes, and electrodes are metal plates to which you can apply voltages to realize electric fields. Okay, So you have electrostatic fields and a magnetic field, and together the electrostatic fields give you confinement in the z direction, and in combination with the magnetic field you get a radial confinement.
So that's what happens in the
Where?
Google IBM.
No, this is completely different. So this is something, if you want to learn more about, so this, there is no commercial company that uses this for a quantum computer. This kind of trap is used for a quantum computer. This is more academic in universities. If you want to learn more about this, the company you have to look up is a company called Honeywell. Have you heard of Honeywell? Okay, so Honeywell has a quantum computing division. It's actually now an independent company. I can write it down for you if you want to look it up. So you should look up a company called Quantinuum. Okay, that's the company that basically emerged from Honeywell and works with ion trap quantum computers. Okay, so these are two different ways to trap ions, and want to see. Yeah, so now that we have some mechanism to trap ions, let's come to that question that what's your name? Athar. The question that Athar asked about how do we encode qubits, right? So the idea is that, have you ever looked at in your school the spectrum of a hydrogen atom, like in textbooks? You have? So you know that the energy levels of an electron are discrete, okay, in a hydrogen atom, right? And so basically, and that too, they are not uniformly spaced. They are basically spaced unevenly. There is a 1 by n square kind of scaling of the energies, right? So basically you have something like, you have the lowest energy state, and then you have the next state, and then you have the next state, and then they keep coming closer and closer and closer, right? Something like this. This is what it looks like, right? So people don't use hydrogen for quantum computing, but I want to take this as a template for energy levels, okay? And basically tell you the point that I can choose two electronic levels, okay, that I can control or make them, if I can make an electron transition very cleanly and controllably between two electronic levels, and these two electronic levels have some nice properties, right? Then I can use those two states of the electron, whether it's in, say, this state or in that state, okay, as the two levels of my qubit, okay? So it's basically the energy levels of the electron, okay, attached to the atom, that actually serve as my qubit states in this particular case, right? It's the same idea that if I want to toss a coin, right, when you play cricket, you don't always only toss a coin, you also do mountains or plains, right? So, and that's also an encoding of a bit, okay? If it falls as mountains, you get head. If it falls as plains, you get tail. So there are multiple ways to encode a qubit, and this is one particular way to encode a qubit, okay? So this is how you can encode qubits in electronic energy levels, and more real world atoms have more complicated energy structures. In fact, you will quickly realize in school that this is not really the, not in school, in college, that this is not the entire story for the hydrogen spectrum, okay? There are many corrections, many different changes, and these levels are even more complicated in structure, okay? So I'll show you a prototypical energy level diagram for the different states, okay? Looks something like this, okay? So these are different states that the electron in an atom can occupy, okay? So basically what this means is that if the electron is in every line that I draw here is a particular electronic orbital, okay? It's a particular shape of the electron probability density that can be occupied, and by having a laser or a microwave field, depending on which levels I want to couple to, I can basically take the electron, excite the electron into a different atomic orbital, basically, okay? And if I can do this in a controllable and reliable way between two specific target levels, I have my qubit, okay? That's basically what is being shown over here. So this is, and the reason we choose something like beryllium, calcium, ytterbium, so in your periodic table you have beryllium, magnesium, calcium. What comes next? Strontium, right? Barium. So these are the ones that if I remove electron so that I get the ion, right? Then I have a single valence electron. So they become more hydrogen-like, okay? And that is why you choose those group of elements in order to for ion trapping. Okay, ytterbium is somewhere else, but it has a similar structure. Okay,
So why?
because then it's the structure is easy enough for us to manipulate and use for quantum applications. That's a different story. First of all, in this case, I need to be able to remove one electron and then it should become hydrogen-like, right? I need the positive charge to be able to trap it, right? So, right. So, but in terms of more generally, why is hydrogen not used? I'm not entirely sure what the answer to that is. I have to think about that. Not sure. Yeah. That's possible. Or maybe the kind of, yeah, I mean, there's also things about, it's maybe too lightweight, like you said, or maybe the electronic levels, the kind of laser systems you need to manipulate might be not very easy to make. I'm not really sure about that. But people, if you want to build, there are other technologies where you use neutral atoms to build quantum computers, and what they use there are rubidium, cesium, the ones, one column before beryllium, magnesium. Yeah, valence. Yeah, so they have these are again hydrogen-like atoms in the sense that they have one valence shell electron, but then they are not just in the principal quantum number 1 or 2. There further down the line. Yeah.
Also, so you take two energy levels. Can you take like three energy levels?
And make a Qubit? Yes, you can. So there are different systems where you can take. If you have 3 long-lived levels and they have good properties, you can make a Qubit. I think there was an experiment 2 years back where they demonstrated a 10-level system with a single calcium ion. So you can do things like that. Okay, and people, when I say calcium, there's not just one type of calcium. There are isotopes and things like that. So there are different varieties of calcium give you different advantages for various applications, right? So, and here what I want to illustrate is that the ground state itself, if you do more atomic physics, you will realize that there are multiple states in there, okay, and then you can separate them using, for example, a magnetic field, okay. There's something called the Zeeman effect. Have you heard of this? So you can basically get some energy difference, and then you can encode your qubit as a ground qubit, for example, okay. So I would call this my state 1 and state 0, for example, okay, or the other way around, depending on what you want. Or I could use something, so, and the separation there can be of the order of a few gigahertz or maybe even as low as megahertz sometimes, and so on. Or I could use something that is that is much further away, more excited than this state, and I could use these 2 states to encode a qubit. This would be 0 and this would be 1, okay. And not every atom gives you every possible encoding. There are some atoms that are so good that you can do multiple types, okay, but this is more like a general picture. This really does not correspond to one particular atom, okay. It's more like a schematic, okay. So there are multiple possible encodings possible for a qubit, okay. So now I want to, so I have like another 10-15 minutes. I want to quickly tell you, for example, how you could do some of the operations that we were talking about. For example, how do you reset, okay, things like that. So I want to show you one particular energy level diagram for a real atom. So this is for a beryllium ion, okay. So this is what it looks like, say, in a trap that looks like this, okay, in the penning trap, right. So that rightmost picture over there, right. So basically that one, okay. Every beryllium ion there has a level structure that looks like this, okay. And the idea here is that your qubit is encoded here. It's called down and up instead of 0 and 1, but it's encoded in 2 of these ground levels. And the way you manipulate the qubit is by shining different types of lasers for different applications, for different parts of a information processing protocol, okay. So over here, for example, you have all of these other energy levels of the electron that you could potentially exploit in order to get the desired operations on your qubit. So one example I'll tell you is that let's say that I want to measure the qubit. Okay, what one would do is take this green laser over here, okay, and shine it and couple this up state with and excite the electron to that state over there. That's an excited state, okay. And there are rules for driving transitions with lasers of different polarizations that you can exploit, okay. So lasers of certain polarizations can only drive specific transitions, okay, they can't drive other transitions. So because of these conditions, what will happen is that this laser with this energy difference can only, with this frequency, can only drive that transition, and it will not really drive that transition so much, okay. So if I am now in the state up, right, on my imaging objective, as I go up, the ion will try to come down. This state has some lifetime, okay, it won't be there all the time, it will decay, and when it decays, it emits light, okay, and you collect that light, and when you collect that fluorescence from the ion, you know that the ion is in the up state, okay. So that's how you actually read out the state of the qubit. If you did not get any light, let's say your qubit was in state down and you did the same protocol, if you don't get any light, then that way you know that the ion is not in the state up, so it must be in the state 0. So this is an example of measuring a qubit basically, okay. So that's one operation that we discussed as being critical for building a good quantum computer, right. So this is how one could, for example, measure a qubit. What was the other operation that we talked about? Manipulate, right. So over here it turns out that for this particular ion, what you can do is, you see the energy difference, okay, the energy difference you can always convert into a frequency. Energy is measured in joules, but the energy difference between different energy levels you can always write as h bar times a frequency, where h bar is Planck's constant by 2 pi, okay, and that way anything in joules you can convert into a frequency. So the energy difference here is of the order of 100 gigahertz. So what that means is, multiply this with the value of h by 2 pi, where h is Planck's constant, and that will give you the energy difference in joules, okay. So what you can do here is, you can shine a microwave source, you can apply a microwave source, and that was already kind of indicated here. See, in this setup there is a microwave, right, and this microwave is at 124 gigahertz, like the splitting between these levels. And because the radiation is resonant to the energy difference between the transitions, it can basically take you from down to up, okay. And based on the phase of this radiation, I can access all the different points on the Bloch sphere, okay. So that's what happens over here, okay. So that's the way that one could in principle manipulate, okay. Remember, we wanted to access all these different points on the Bloch sphere, starting from 0 and all the way to 1, and by shining microwave radiation through some antenna like this, you can basically couple down to up and so on, okay. So that's one way that we can manipulate the qubits.
So, you said that you were encoding the qubits, sir. I thought qubits were really small.
So an encoding is an understanding between, between you and the device, that, even with a coin, right, it's your interpretation that head is 0 and tail is 1, right. So an encoding is nothing but an interpretation that I'm going to call this state as 0 and I'm going to call that state as 1, okay. So it's just an interpretation.
Interpretation, but how is it going to quantum computers?
What do you mean by work?
You're supposed to make these qubits do something. You're supposed to get the output.
Yes. So, so that do something part is where we manipulate the qubits, and the way you can manipulate this particular qubit is by putting in microwave radiation, because that will basically couple the two levels together. And by, what the microwave will allow you to do this is, on this sphere, the microwave will give you an axis of rotation, okay. And so you start from up and then you rotate about that axis, and basically you can go to any other state that you want by shining for an appropriate duration the microwave. If I shine it for long enough, it will go all the way. If I shine it for even longer, it will go all the way again and come back up, right. So it depends on, you need to calibrate and measure for how long you need to apply these signals, right. And the other thing that you said was about readout, and for that, what I was trying to point out is that you have all these other levels, and so I can shine lasers that couple one of these states to one of those levels, right? And then that state has some lifetime. If I excite the electron there, like I said, not every state is perfectly stable. Some like to decay. This is a state that likes to decay, and it will just decay back to the same state again. So it keeps going on what is called a cycling transition. It goes up, decays, goes up, decays. Okay. So if I shine this light even for 5 milliseconds or so, I will collect thousands of photons. Okay. If the state was here, right? So now an interesting question is, let's say that I prepare a superposition of down and up. So I'm actually on a state that's on the equator of the Bloch sphere, right? And then I try to measure what will happen over here. Okay. So I couple up to some state, and then I put my camera and try to look for photons. What will happen is, in half my experimental runs, I will detect photons. In the remaining half of the experimental runs, I will not detect photons. And that is the experimental implementation of the fact that you collapse into the state 0 or 1 with probability half if you're in an equal superposition of 0 and 1, right? So in the real experiment, what they do is they repeat an experiment 100 times, okay, and then say 60% of the time they measure it in state up, and in 40% of the time they measure it in state down. Then they know that mod A square for this state was 60 and mod B square for this state was 40. That's how they measure the probabilities associated with the state. Okay, so I had more to say. How are we doing for time? I have 10 more minutes. So, okay, so let's see. Yeah, so now there's one thing I want to quickly introduce after just having some water, which is I haven't still told you how these different qubits interact with each other. How do you think that's possible? I just want you to think about it. How can I make this qubit? What do they share, or how can they feel each other's presence and interact? Well, given the device that you have, how can I make them feel each other's presence? They already feel each other's presence. How? Repulsion, right? Coulomb repulsion. That's how they feel it, and we will use that. So the point is that they form these very nice equilibrium crystals, right? You form, and this I told you came from a balance of the Coulomb repulsion and the harmonic confinement, right? But the ions there's always some motion associated with the ions. So there is always some small amplitude motion about the equilibrium position. And the point is that if you think about it, for any generic curve, okay, if I have some potential V of x, okay, and I'm at the minima of that potential, okay, that's what an equilibrium configuration is. It is the minimum point of a potential energy surface, right? About that minimum, right, because it's a minimum, the first derivative vanishes, right? And so what you have as the lowest order correction to that minimum value is the second derivative, right? And for a minimum, the second derivative is always, there's a sign, positive, right? So what that means is, very close to a minimum for any generic function, it always looks kind of like a parabola or a multi-dimensional parabola if I have more variables, right? So it always looks quadratic, okay, because that's the first correction, that's the first approximation. And so the potential near a minimum always looks like some half kx square. What is that the potential for? Spring. Okay, it's a harmonic oscillator. So, and that's why harmonic oscillators always come up in physics. There are two reasons for that. One is what I said. The other is that's basically the only system that most of us know how to solve. Okay, so we try to convert everything into harmonic oscillators because then they give you nice exact results that you can actually work with, right? And so the same thing happens here, but the correct analogy is that you should really think of this as a bunch of masses on springs with other springs attached between the different masses, right? So let's say that I have two masses and they're attached to walls with a spring and there's a spring between them, right? Then you can't describe the motion of every mass individually as a harmonic oscillator, okay? There are actually collective shared modes that are actually the harmonic oscillators. The masses can go together like this, right? Or they could stretch and bend like the modes of a molecule, right? So you could have a mode like this and so on. So the point is that they are harmonic oscillators, but not the individual motions of each molecule or each atom. Okay, what is a harmonic oscillator is some collective degree of freedom of the system. Okay, and so there is a collective motion. There are a variety of collective motions, each of which is some kind of harmonic oscillator. So I want to show you some examples of that. So here, okay, so let me try to play this. So this is for this particular crystal over here, right? This one, and this is actually the top view. What we are going to look at now is the side view. Okay, we are going to look at how it oscillates up and down in this along the z direction. Okay, so these are the first few harmonic modes associated with this crystal. So let me try to play this. Okay, so this top mode here is basically the center of mass mode. That means that all the atoms simply move up and down together. But then there are other harmonic modes of the crystal, and those modes are modes where you have a tilt of the crystal along different directions, and then you have these other modes where you can see further bending of the crystal basically. Okay, and this way all the small amplitude motion around the equilibrium configuration is resolved into a set of modes, okay, into a set of normal modes that happen at different frequencies. Okay, so forget about the axis of this plot. The main take home message is that you have distinct frequencies of normal modes, and each one of this is associated with a particular frequency of motion. Okay, and that comes from the fact that near the equilibrium it always looks like a harmonic potential, and you have these collective oscillations that are harmonic oscillators. The fun fact with these crystals is that because of the magnetic field, the motion in plane is harmonic, but it's not simple harmonic. Okay, and that's I don't think it's something you need to know about right now, but I think it's still fun to look at the modes. So I have these modes here, so I want to play this and show you. So these are the different possible modes, and I wanted to see how the modes in plane actually move around, okay, for different possible harmonic motions in plane. So that's one set of modes, and then there's also another set of modes over here that actually have some kind of opposite sense of rotation. Okay, so these are all different possible modes associated with the in-plane motion. And because they're so complicated, we usually don't worry about it, and we only work with the motion in the z direction. Okay, but why did I talk about motion so much? I'll take just 2 minutes to explain this, which is that what you can do with the motion is couple the ions with the motion. Okay, so and the way that works is, you know, the laser. I said that you can basically change the electronic state with the laser, but what's the electric field of a traveling wave? The electric field of a traveling wave looks like E naught cos, if it's traveling in the z direction, kz minus omega t. Okay, that's what it looks like. And what that means is that the phase of the laser field, okay, the cos, okay, depends on that the ion experiences depends on where the ion is in the z direction, right? And so as the ion moves up and down, if the it samples different phases of the laser, okay, and because of that, in some sense, the axis of rotation that you're applying to the ion, okay, keeps changing based on where the ion is located. And in that way, the electronic state of the ion gets correlated with the motion. But like I said, the motion of one ion is not just its own motion, it's correlated with the motion of other ions, right? And that way, there's some shared phase that shows up, and that's what causes two distant qubits to interact with each other through their shared motion. Okay, so a setup would typically look something like this, right? So here I'm showing a bunch of ions, and you have two lasers that form some lattice in the z direction, and as the ions move up and down, they sample different maxima and minima associated with the lattice, and because they move sort of together, their motional states get kind of correlated with each other. And that's the, let's say, the vanilla model of how you can actually use the shared motion of the ion by coupling it to a laser to entangle the electronic states of the ions together. It's the ion motion that actually helps you to make them interact with each other. Okay, I know in the end it was a bit fast, but you know, we only have so much time, so I had to rush in the end. But I hope that you got a feeling of how at least one platform operates, and this is a very emerging area. This is just one out of, Google and IBM don't use this, right? They use superconducting qubits. That's another story on its own. But I hope that this will give you the seed to actually go and read more about these different platforms. And the take home message is, quantum computing is not just about zeros and ones on paper. Okay, there's actually a lot of physics going on in the background that we actually need to understand if you want to make these devices work in practice. Okay, so I hope you enjoyed it, and thanks a lot for this chance.
Swayam Prabha, Digital India, Educated India.